Thank you for waiting. Doctor, can you please start sharing your presentation, please?
Okay, can you see my screen?
Yes, thank you.
Excellent.
Okay, so I'm gonna introduce you real quick. So good evening, everybody. Welcome to this conference titled Supernova Model Discrimination with Hyper-Kamiokande, presented by Dr. Jost Migenda. Dr. Migenda is a research associate in the experimental particle and astroparticle physics group at King's College London. After graduating from TU Munich with a Master of Science in Nuclear Particle and Astrophysics, they did their PhD at the University of Sheffield, investigating Hyper-Kamiokande's ability to distinguish between different computer simulations of supernova. At King's, they work on astrophysics and DAQ development for Hyper-Kamiokande and Super-Kamiokande, and they are a member of SNews 2.0, which uses neutrino detectors around the world to provide an early warning to astronomers when the next galactic supernova is coming. They also organize the EPAP seminar series. The Q&A will be taking place at the end of the presentation, but during the presentation, you will be able to send the questions through the chat or in the comment section in Facebook, and the doctor will be answering them at the end. We really appreciate you accepting our invitation to this series of conferences, and we thank you all in the public for being here with us today, and hope you enjoy this time with the doctor.
Okay, thank you. So, buenas tardes a todos. Gracias por la invitación. Lamentablemente solo hablo un poquito de español y por lo tanto voy a continuar en inglés. So I will continue in English. So I am going to talk about supernova model discrimination with Hyper-Kamiokande. And you are, after listening to all the talks over the past 2 days, you're really well prepared for this. But I want to give just a brief reminder of what Hyper-Kamiokande is and what supernova neutrinos are. Before I talk about research itself, but also the way from starting a PhD to actually having this published paper in hand. So Hyper-Kamiokande, you know, is the third experiment in this long-running Japanese series of neutrino experiments that started in the 1980s with Kamiokande, whose leader, Koshiba-san, received a Nobel Prize in 2002 for detecting neutrinos from a supernova 1987A, and basically starting neutrino astronomy. So it was incredibly successful. And yet after about 10 years, they found that they were hitting the limit of what they could do with a detector of that size. So they built an even bigger detector called Super-Kamiokande. It's a very creative name, I know. And Super-Kamiokande is now over 25 years old. So it's older than many of the new PhD students working on it. And it also has been incredibly successful. And you've heard yesterday about the 2015 Nobel Prize for discovering neutrino oscillations, which show that neutrinos have mass. So Super-Kamiokande is still running today, but again, we're getting close to the limit of what we can do with a detector of that size. So our next step will be to build this even bigger detector called Hyper-Kamiokande. And details of the Nobel Prize still to be determined. Now Hyper-Kamiokande will be 71 meters high, 68 meters in diameter, and it will be built deep underground, inside a mountain, under 650 meters of rock to shield it against cosmic rays that are raining down from the atmosphere. And I know these numbers kind of sound impressive, but to give you a better sense of scale, I would like to compare this Hyper-K, to the size of a building, a quite famous building in London called Tower Bridge. And you can see this whole bridge with all the cars and buses on there would just about fit into our detector, deep in a cavern underground. So I hope that gives you kind of a sense of the scale of this detector. Now, inside the detector, there will be ultra pure water. And this is a photo from inside Super-Kamiokande. You can see there's people on boats here repairing the detector. And all over the inside walls, you have these photosensors, which detect Cherenkov light from charged particles that are created by neutrino interactions. And you get these Cherenkov rings shown here at the bottom. Like from a muon, you get this very clean ring, whereas from an electron, the ring is much more kind of fuzzy. And of course, you've learned in the first talk on Wednesday how Cherenkov radiation is created. So right now, Hyper-Kamiokande was approved last year, and we've started excavating the tunnels. And will, if all goes according to plan, start taking data 6 years from now. So Hyper-Kamiokande has over 400 members from 19 countries now, including, of course, Mexico. And I have to say, you picked a great time to join Hyper-Kamiokande, because all the excitement starts now. So now let's talk a little bit about supernova neutrinos and what we will be able to do with Hyper-Kamiokande. And this is a remnant of a supernova that exploded almost 1,000 years ago. And it's called the Crab Nebula. Now, supernovae produce all sorts of different signals. They produce the electromagnetic signal, like the bright light that people usually think of first when you tell them about supernovae. And this light itself will be as bright as a whole galaxy of billions of stars together. But you can see here the luminosity, and you can see the luminosity on the y-axis is quite low. So there's much more energy emitted in gravitational waves. And of course, most of the energy, 99% of the total energy, is in the form of neutrinos. And these are emitted a couple of hours before the optical signal becomes visible. So studying these neutrinos is really our best way to discover what goes on deep inside the supernova as it explodes. And so far, we've observed just one supernova with neutrinos, the famous supernova 1987A, where we saw about 24 neutrinos, and half of them, shown in yellow here, in the original Kamiokande detector. And this showed us that this basic picture of how a supernova might explode that physicists had before then looked pretty much correct. So we could tell that if we saw 24 neutrinos, the total number of neutrinos emitted must be extremely large. It must be something like 10 to the 58 neutrinos, with a total energy of 10 to the 53 ergs, which is 99% of the energy of the whole supernova. And we also noticed that the neutrinos arrived on Earth a few hours before the light. Now, since then, there have been over, I think, 1,600 papers written about these 24 neutrinos. Some about neutrinos, some about supernovae, but also many about completely different particles. Because if we have seen that the neutrino emission takes place for about 10 or 12 seconds. And so what that tells us is that any other particle that theoretical physicists invent, like axions or like some dark matter particles, all those can only be produced in very small numbers in a supernova. Because if you were to produce too many of them, they would transport away energy so quickly that there wouldn't be any energy left after 12 seconds or so to produce these neutrinos. So this is a very strict constraint on the properties of hypothetical particles. Now, of course, 24 neutrinos are not enough to tell us how exactly the supernova explodes. So since then, most of what we know, or what we think we know, comes from computer simulations. And the problem is that computer simulations are really difficult because you have to simulate all four fundamental forces: gravity, electromagnetism, the strong force, and the weak force. All of this in an extreme, under extreme conditions that are highly relativistic, extreme temperatures and pressures that are sometimes impossible to recreate in a lab on Earth. So it's really difficult to do these simulations, even with the biggest supercomputers we have. So when I started my PhD, there was this paper by one of the world's leading supernova modeling groups. And they wrote that, quote, "There is a long list of numerical challenges and code verification issues yet to be met." So effectively, we have to use these approximations because we don't have enough computing power, and we're not quite sure how good they are. And then they say, results of different groups are still too far apart. So different groups with their own code, with their own approximations to be able to do these calculations at all, find quite different results, even for the same star. So there are a lot of uncertainties in these computer simulations. And we really need to observe supernova neutrinos to figure it out. But the basic picture, the basic picture is something that most of these simulations agree on. So I want to talk about that a little bit here. And in these pictures, the kind of top part will have these arrows that show how the matter is moving inside the star. And then at the bottom, I will have these ghosts, which stand for neutrinos. And these will show where neutrinos are produced and how they behave. And we start with this massive star that's at least 8 times the mass of our sun, which, as you heard yesterday, will fuse hydrogen to helium, and then onwards to carbon and oxygen and silicon and so on, until it finally produces iron. And the iron cannot fuse together, so it just accretes here in the center of the star. And when you have enough iron, about 1.4 or 1.5 solar masses, this iron core becomes unstable. It collapses under its own gravity. And at that point, the electrons in there are pressed into the nuclei. They fuse with protons to form neutrons and neutrinos. And these are the neutrinos here. And after about 0.1 seconds, the material in the center of the iron core becomes about as dense as nuclear matter. And at that point, even neutrinos cannot easily escape. You know that neutrinos only interact very weakly, and they can go through as much as a light year of lead. But the matter inside here is so dense that even neutrinos will bounce off the matter and cannot escape easily. So a little bit later, actually the density here becomes denser than nuclear matter. And somewhere at that point, you cannot compress it any further. It hardens, and all the matter that's still infalling is basically hitting a wall and is thrown back. And these neutrinos in the center are still trapped, but this infalling matter hits the wall, bounces back, and you get this outgoing shock wave. And just behind this shock wave, it uses up most of its energy to split up the iron nuclei into free neutrons and protons. And these free protons, then while the neutrinos in this middle are still trapped, these free protons capture all the remaining electrons. So you get this sudden burst of neutrinos here, which are produced. And since they are a little bit outside of the core, they can actually escape. And if you look at the neutrino emission over time, what you see is this very brief but intense peak of neutrinos right here. So then the shock wave uses up most of its energy to split up the iron nuclei. So it slows down. And meanwhile, matter from outside is still falling onto the shock front. And you've got various nuclear reactions going on there, producing neutrinos again. And the neutrinos are again escaping. And this is not quite as intense, but it's a steady flow of neutrinos. And if the shock wave kind of moves back and forth, and the rate at which matter falls in onto the shock front, if that varies, the neutrino emission can vary as well. And then, meanwhile, in the center, most of the neutrinos are still trapped, but the first ones are slowly making their way outwards. Some can escape, but a few of them get stuck in this shockwave layer. They interact there, deposit a little bit of energy, and reheat the shockwave. So the shockwave starts to accelerate again, starts to move outwards. And once over the next 10, 20 seconds or so, the neutrinos from the center are slowly making their way outwards. And they are traveling at the speed of light, so they will reach Earth very quickly. But the shockwave is a bit slower, and the shockwave needs hours to reach the surface of the star. And only then, when the shockwave breaks through the surface of the star, only then do we actually see optical light from the explosion. So this is roughly the neutrino emission we'd expect. A very intense peak at the start, a little bit of kind of wiggling back and forth as the shockwave stagnates. And all of this takes just half a second or so. And then over the next 10 or 20 seconds, the neutrinos from the center are escaping, and we're seeing fewer and fewer neutrinos. So that's what we'd expect. Now, how do we detect those neutrinos? And in water, like in Hyper-Kamiokande, there's 4 different ways of detecting these neutrinos, shown on this slide. And the first one is called inverse beta decay. And this is where an anti-neutrino, so the antimatter equivalent of a neutrino, which is why it's on set, hits a proton, so a water nucleus, hydrogen nucleus. And it will turn into a neutron and a positron. And the positron has so much energy that it produces this cone of Cherenkov light. So that's the most common way for neutrinos to interact in water. Then another way is neutrinos scattering on an electron in one of the atoms. So it gives the electron a little kick, like billiard balls. And the electron then slows down by emitting Cherenkov radiation. And then neutrinos or antineutrinos can interact on an oxygen nucleus, shown here. And they produce either an electron or, for antineutrinos, a positron, which again sends out this cone of Cherenkov light. And the oxygen nucleus turns into fluorine or nitrogen. So these are 4 different ways of neutrinos interacting in water. And in Hyper-Kamiokande, you can see here the number of events over the energy we'd expect. And this is for different supernova models. But you can see the black line here, which is the antineutrino interacting on a proton. So inverse beta decay, this is the most common channel by far. Then you've got the interactions on oxygen, shown in pink and in blue. And finally, in red, you have neutrino electron scattering. And this is mostly at low energies, so it's a bit harder to see. But it's still quite interesting, because so overall we see these tens of thousands of events from a typical supernova within our Milky Way. And of these, maybe 1,000 or so are electron scattering. But these are very interesting because they can actually point back to the direction the neutrino was coming from. So they can tell us approximately where in the sky the supernova was. So we can warn astronomers, the supernova is happening about there, get ready and point your telescopes. And with all these events, and for every one of them, we will be able to reconstruct the time and the energy of the event. And this gives us a really good picture where we can see kind of millisecond by millisecond how many neutrinos are emitted and at what energies. So we can tell precisely how the supernova explodes. So that's supernova neutrinos in Hyper-Kamiokande. And next, for the next 20 minutes or so, I want to talk a bit about how we actually use this. And I want to explain the kind of path from the start of my PhD to getting this paper published. And a picture I found that I really liked is this PhD bathtub by a German astronomer called Victoria Greenberg. And this is kind of the typical cycle of a PhD. So at the beginning, you're very excited. You see this cool project, you jump right in, and then you notice the water is much deeper and much colder than you thought. And it's actually really, really difficult. And you struggle. And this is the middle part of a PhD can be very terrifying. But finally, when you get to the end, it's still hard work to get up there. But you know, the end is in sight, and you will finally get out and win the trophy. So for me, I grew up in Germany, near Berlin, and then I studied particle and astrophysics in Munich, where I did my bachelor's and master's degree, and moved to the UK afterwards. And so for my master's degree already, I did some research on supernova neutrinos in Hyper-Kamiokande. So when I found the university in Sheffield advertising this PhD topic, which was almost exactly what I already did in my master's, I was really excited. So I contacted them, applied, got the topic, and started my PhD. And at that time, I was really here at the start of the bathtub. I was very excited. The project looked amazing. And then I jumped in and quickly noticed, you will see the topic says supernova neutrinos in Titus and Hyper-K. Now, you probably don't have heard of Titus. And that's because Titus was a proposed detector that got canceled pretty soon afterwards. So I had to change the topic. And I had to switch from Titus and Hyper-K to Hyper-K and Dune. And Dune is another large neutrino experiment that's being built in the US right now. And then, of course, it just says supernova neutrinos. And that's very vague. So I was thinking about, okay, what exactly do I want to do? And then I tried a few different things, which didn't work out or which turned out to be too easy. So it's not worth a full PhD. And in the end, I decided to do supernova model discrimination. Originally with Hyper-K and Dune, both together. But after working on it for a while, I noticed that I wasn't, working on Dune was very slow. I was not making enough progress, and I wouldn't get any good results from that in the limited time I had. So I had to talk to my supervisor, and we had to change the topic yet again until it finally became the topic that we know today. And this was really me being in this middle here, in this long drowning phase where everything's much more difficult than I thought. And this is a very long phase. This took more than half the PhD for me. So, this is really not to scale here. actually, it's more like this. It's this very long middle phase. And while you're right in the middle of it, it feels more like this. You have this long phase and there's no end in sight. And that's really scary. That was really scary for me. Because when I was in it, when I was figuring this stuff out, it didn't look quite as obvious as this series of 4 topics. It was more like, every step of the way, I could have taken a different branch, switched to a different topic. And I was never quite sure what was the right choice. What should I do next? So that was quite stressful. And it's really important to have a supervisor who is supportive and who helps you figure this stuff out and calm you down when you get too excited or too nervous. And I'm lucky then that I had a really excellent supervisor, I have to say. But over these, I think, two or 3 years spent in this middle phase, there were actually quite a few puzzle pieces I produced. So first off, there was this software for detector simulation, which already existed before I started. And there was some software to reconstruct events and figure out where in the detector and at what time the event had happened. And that also existed, and that was taken from Hyper-Kamiokande. And then I started to work. I think the first thing I worked on during my PhD was energy reconstruction. So figuring out not just where the event was and at what time, but also how much energy it had. And for this, I used the method that was originally developed for Hyper-Kamiokande. But obviously I had to tweak it a bit for the different detector. So that's quite an old method. Didn't involve any of the brand new machine learning techniques you heard about yesterday. Although in the future, I think we will work more on that. And I look forward to seeing your work there. So then, after the energy reconstruction, I worked on an event generator, which takes some neutrino flux from a supernova and figures out, okay, but how many of these neutrinos actually interact in the detector? And what do they produce, what particles? And then to feed something to this event generator, I had to find a few supernova models. And some of them colleagues of mine had already worked on previously. So I got those relatively quickly. But then I was also looking around for more of them. And one I actually found through a happy coincidence. Because I happened to follow someone on Twitter who was doing these supernova simulations. And one day he tweeted about their new paper with some brand new model. So I messaged him and asked him, hey, do you have these neutrino fluxes? Could you give them to me? And he was very, very happy to do that. So I found Twitter actually to be quite useful for getting to know more people in the field. And then something else I discovered while reading one of the papers on the supernova model is I discovered this likelihood function, this statistical tool to tell different supernova models apart. So I had all these puzzle pieces, and after a while, I noticed that these pieces actually started fitting together. And so I had these supernova models that tell me how many neutrinos are produced at what energy. I had the event generator that takes these neutrinos and tells me how many interact in Hyper-K. I had the detector simulation, which takes the events and actually simulates what signal they produce, how much light. And then I had this reconstruction software, which based on the detected signal figures out where the event took place and what energy it had. And finally, I had this likelihood function, which could tell me, based on these events I've reconstructed, which supernova model best describes them. So suddenly, all these pieces were in place, and they fit together. And that was when I reached the end of this long middle phase, where I knew there was still a lot of hard work in front of me, but I could finally see the end. I knew that I would get a good result from this. And then fitting these pieces all together, fixing lots of bugs in the software took most of the last year of my PhD. Now here, I show you the 5 different models I used. And I've named them after their first author, respectively. And what I did then is I picked one of these models. Let's say the couch model here in blue, which has this distribution of the event rate over time. And this is how the mean energy of the events behaves over time. And I just generated 100 random events from this, from this distribution. So one data set, 100 events. I simulate all of them, reconstruct them, and I use this likelihood function here. And what this basically consists of is this one term here in blue, which says, how many events does some model predict at the times and energies that I've reconstructed. And generally, if a model predicts that a lot of events with the time and energy that I observed, there should be a lot of events at those times and energies, then that model has a high likelihood of producing the observed events, right? So you can calculate this likelihood function for each different model, because each model predicts a different distribution of events. And then I can compare 2 of them. So let's compare let's say the couch and the Nakazato model. And if I generate a data set based on the couch model, then obviously the couch model should have a higher likelihood. So the difference between the couch likelihood and the Nakazato likelihood should be positive. And this data set should be somewhere here on the right, somewhere in the positive numbers. Might be very positive, it might be close to 0, depending on how different they are. It should be somewhere on the right end. And then I did this 1,000 different times, produced 1,000 data sets from the couch model. And because you have random fluctuations in these models, you will get a spread of likelihoods. And you can see this here in black. These are the 1,000 data sets generated from the couch model. And you can see most of them are towards the right of this line. But some of them randomly happen to be a bit atypical and look a bit more like Nakazato models. And similarly with the red line, those are 1,000 data sets generated from the Nakazato model. So they should be more likely to be the Nakazato model. So the result, this delta likelihood, should be negative. And indeed, it is for most of them. So we can tell these two models apart quite nicely. And that was, really exciting when I first saw this. And then we could do this for all the 5 models. And you can see for each of them, you can nicely tell them apart. It's very, pretty clear. Although sometimes there is a bit of an overlap. And actually, you can see the biggest overlap is here between the Tambora model in red and the couch model in black. And if we go back just to this slide, the couch model in blue and the Tambora model in this kind of light blue. And you see they're very, very similar. So they will be very hard to tell apart. And we might confuse them for each other. So that's about what we'd expect. And finally, what we can do instead of comparing 2 models at a time, we can compare all 5 by saying, for each data set, which of the 5 models has the highest likelihood? And then you can make a table like this, where you have the true model on the left. And for example, for the couch model here, we made 1,000 data sets, and about 800 of them were identified correctly as the couch model. And about 120 were misidentified as Tambora because they look pretty similar. But still, 80% identified correctly. And for some of the other models, you can see 96 to almost 98% identified correctly. And this is based on just 100 events, which is pretty nice. Of course, if you have more events, you should get better at identifying the model. And indeed, if with 300 events, you can see we get to 98, 99.9, almost 100% accuracy in identifying these different models. And remember that Hyper-K is really big. And 300 events in Hyper-K, we would get that from a supernova anywhere within the Milky Way, or even a bit outside the Milky Way, like in the Large Magellanic Cloud, 150,000 light years away. So that was the result of my PhD, and I'm very proud of this, of course. And then I had to write it all up, and this is my PhD thesis, and you can find it on the archive if you want to read it. So I submitted this end of 2019, finished my PhD in February of 2020. And just a few days later, also in February of 2020, the Hyper-Kamiokande experiment was officially approved. So we got the budget from the Japanese government and we could start construction. So that was really good timing. And you can imagine I was very excited because I knew that this would become the first Hyper-K physics paper. Now, the downside of being the first is nobody's done it before. There are no procedures. There's no, you don't know how to do all this. And also because we were just about to start construction, it was an incredibly busy time for everyone. So people were negotiating with companies, preparing for construction, and people didn't have a lot of time to figure out the formalities of how do we publish a paper as a collaboration. So it took a while to figure all this stuff out. And over the next year or so, I started writing a draft of this paper. And we formed this review committee, which was me, my supervisor, and 2 other physicists from Hyper-Kamiokande. And then this paper committee reviewed what I had written, asked me to change a few things, add a new figure here and there, and so on. And when they thought it was good, we sent it to the Hyper-Kamiokande Astro working group. They reviewed it, asked me to make some changes, and when they were all happy, we sent it to the whole Hyper-Kamiokande collaboration for their comments. So I made some changes again. And when they were happy, that was in January of this year, we could finally send it out to the journal, which finds another reviewer, this time someone outside of the Hyper-K collaboration, who was not involved with the paper before, and asked them for comments. And then again, I had to change a few things until finally, this summer, the actual paper was published. And you can see on the author list, all members of the Hyper-Kamiokande collaboration, all, I think, 500 people on this paper, which is only fair because all of them contributed in some way. Without them, there would be no Hyper-Kamiokande, and I wouldn't be able to do this. So you can see all the names, you can see my name, you can see the names of some of the Mexican academics on Hyper-K. And I think it's very exciting that since then, in just the last few months, several more have joined, and I am happy to have you in the collaboration, and look forward to seeing what we all can do together as Hyper-Kamiokande starts. So thank you very much. Muchas gracias. And as our Japanese colleagues would say, arigatou gozaimasu.
Thank you very much. I don't know if there are any questions in the public. Okay, so Brian asks if the water inside the tank has to be purified constantly due to the neutrino-oxygen interaction.
So yeah, the water is constantly purified. We circulate, I don't know how many hundreds of tons of water every hour. And some of that is because of, for example, bacteria growing in the water. Some of it is from radon that's in the surrounding rock, and that kind of diffuses into the water. So yeah, we have to constantly recirculate the water, clean up the water. And we can even see that between the top of the detector and the bottom of the detector, so between where we add fresh water and where we take out the older water to clean it again, we can see that there's a big difference in the water quality already. So yeah, absolutely, you have to clean it. Actually, my supervisor once told me when he was inside Super-Kamiokande in a boat doing maintenance work, he had a little bit of a break, so he leaned back in the boat, and some of his long hair fell in the water in the tank, and the water was so pure that it didn't contain any salts. So it sucked all the minerals, all the nutrients out of his hair. And later that evening, his whole skin on his head was itching like mad because it had sucked away all the nutrients, all the minerals. So yeah, it's ultra pure water. And we need to do a lot of work to keep it that clean. It's a very good question.
Thank you very much. Someone has a question. I don't know if you want to speak up.
Oh, well, thank you. Well, more than anything, I just want to thank publicly Jost for presenting out today, and it's a pleasure, and I'd like to have him here and to talk to the students. Just thank you, Jost, again for being here. That's it.
Thank you for having me. It's always a pleasure to talk about this work and share kind of what it's like to do a PhD and to work on an experiment like this.
Yeah, that's awesome. I hope some of these students today will take into this journey of doing a PhD. That'll be a great thing to have. Thank you.
Actually, if one of the students are listening now, if you start a PhD on Hyper-K at some point, and I see you at a collaboration meeting, please come up and say hi. I'd love to meet you.
Thank you. I think there's a couple of questions more. I think he's referring to the models you talked about earlier on, but Jose Pablo wants to know what's the difference between each of the models.
Between what?
The models, I think the ones you showed.
Between these 5 models. So the difference between these 5 models?
I think so, Jose Pablo.
Okay.
I don't know if you can say something.
Okay, so these models were by different, so there are different groups all over the world. So for example, Couch is in the US, Nakazato in Japan, Irene Tambora was in Germany at the time. And then you have other groups in Japan and the US. And each of these groups has their own simulation code, where they have differences in, so I said it's really hard to include absolutely all of the physics in these simulations, because we just don't have the computing power to do it all. So they use different approximations to make this task a bit simpler. So for example, some of them, like the Couch and Nakazato model I used here, they assume that the whole explosion is spherically symmetric, which makes it a lot easier to simulate. So they can, for example, simulate stars with lots of different masses and compare them. While the Tambora one was much more complicated simulation. So they tried to make it as accurate as they possibly could. But that means they were only able to simulate this one single star and not hundreds of different stars with different masses. So yeah, there's different ways of approaching this problem, and it depends on what you want to do.
Thank you. Rodrigo has a similar question, and he wants to know what is the main difference between the Couch and Nakamura model, and if your results mean that it's highly probable that we will know which one is the correct model with a single supernova.
So the the difference between the couch and the Nakazato model, I'm not sure off the top of my head. So at that point it gets, so they are both these spherically symmetric models. And then it gets quite technical in terms of, for example, what equation of state you use, which means basically how much the this iron core I talked about, how much that can collapse down before it becomes incompressible. And we don't know that very well. But then also in terms of what neutrino interactions in the supernova you include and which ones you don't, and so on. So that, I think that gets very technical, the difference between those two. And then the second part was, can we tell which one is correct based on just one supernova? And well, it's hard to say because so in principle, you know, you can see we get this 98%, almost 100% accuracy in telling these models apart. But of course, you know, all of these models use some approximations. So we know that neither of them is actually the true model. But I think once we observe a supernova with Hyper-Kamiokande, having this, being able to compare this with lots of different models, and then figuring out, you know, even if none of them is quite the right one, which is most similar, and then focusing on that one and trying to modify it and make it more accurate. I think that's going to be the approach.
Okay, thank you. There is a question in German. I think it says how many milliseconds it takes to test see the neutrinos. I don't know if you want to read it. I'm gonna send it to you.
Got it. Yeah, so all of this all of this process I talked about here takes place in about half a second or so until the supernova kind of starts, and then takes 10, 20 or so seconds for the rest of the neutrinos in the center to escape. So yeah, and it varies a bit between models. So for some it might just be, you know, 0.2 or 0.3 seconds. For others it might take as much as 1 second for this shock wave to reignite. But yeah, typically for the whole neutrino signal, we're talking about tens of seconds.
Thank you. I think there's 2 more questions. At what temperature is the pure water in the Super-Kamiokande, and how it affects the results on the experiments?
So the water is about 13.5 degrees. And in principle for the neutrinos, it doesn't matter what temperature the water is, because the neutrino only sees the single electron or proton that it interacts with. And the thermal energy of that proton is much lower. it's almost negligible. But where it makes a difference is when you consider these photosensors, because these photosensors produce what's called dark noise. So even if there's no light shining on them, they will occasionally still produce a signal, background noise. And the warmer the water gets, the more of this background you have. So you want the water to be relatively cool, so you get less background and you can see lower energy neutrinos.
Okay, thank you. And last question. Sergio Perez found on the past days your GitHub and installed your package Essence tools. And he wants to know which would be the learning route to learn how to use the package correctly.
So the easiest way is probably to look at the README file in the repository, or at the documentation. So I have a PDF that's about maybe 20 pages or so that shows you how to install it, how to use it, and then explains some of the details behind it, and talks about these different models and so on. So yeah, have a look at this, and if you have any questions after that, feel free to contact me. I've got I think my email address is on that PDF as well.
Okay, thank you. So I think there is no more questions. So we would like.
Always happy to hear from. Sorry, always happy to hear from people who use this software.
Yeah. So if there's nothing left, we thank you very much for being here with us today. And we thank everyone on the organizing team, from the students, SAIFI and CapTech, and also the Outreach Hyper-Kamiokande in Mexico team. We also thank the doctors who enlightened us with their presentations during this week, and everyone who joined us. And thank you, Dr. Migenda, for joining us today. We remind you to follow all the social media on Twitter, Instagram, Facebook, TikTok, and YouTube, where you will be able to get to know updates on the collaboration and other important information regarding future events. Thank you all for coming.